So looking at page 40, we're talking about the hypergeometric probability distribution. So you have this little background information here. A sample of size n is randomly selected without replacement. That's the key term. All right, without replacement from a population of n items. In the population, k items can be classified as successes and n minus k can be classified as failures. Hypergeometric random variable, number of successes that result from a hypergeometric experiment, which shouldn't be overly surprising. So here's the formula. And it's a pretty funky looking formula, but it's not terrible to work with. I'm going to take you through an example involving a table approach, just so you can kind of understand that this isn't really new, even though you see this formula, it makes it seem like it is. Right? So the example, suppose there are 50 officers, 10 female and 40 male. Suppose 20 of them will be promoted. Right? X would represent the number of female promotions. The hypergeometric model would be this, right? So what I would be saying here essentially is I'm looking for the haves and the needs, right? So I'll just kind of jot it down up here. So we have the haves and the needs. So we have we'll start with female because that's the question of interest. Female, male. They gave it to us in reverse order, but we have 10 female, 40 male officers. 20 of them are going to be promoted. We just don't know if it's going to be all the females and 10 of the males, or if it's going to be, let's say 5 females and 15 males. The breakdown is uncertain. So we designate a variable I to represent the instances where a female is promoted. So then everyone else that is promoted, because we have a total of 20 that are promoted, everyone else out of that 20 has to be male, right? And then we look at that, so that's the numerator. The denominator is just any number of 20-person combinations that you can get from 50 people, right? So think of this as the sample space. And the top, that would give us the number of instances where, depending on what I is, it would satisfy the whatever criteria is decided upon, right? So what I do here in this table is I look at all the different possibilities that you can have for I, right? It has to be capped at 10 because there's only 10 female officers. So I would go into statistics, get rid of this stuff, pop in 0 through 10. I'll do fill with a formula. Oops, I keep hitting the wrong thing. Fill with a formula, grab that first one. That goes from 1 to 10. If I wanted to go from 0 instead of 1, I'd just subtract 1 from this. That would give me 0 to 9. So I'd make this an 11. And that'll get me 0 to 10. All right. Then for my frequency, fill with a formula. All right, empty. And I'll go into my toolbox, probability, combinatorics, and I'll grab my combination function here. And I'm essentially just putting in this stuff. So 10, my I values are in V1, so shift alpha, division 1, toolbox, now 40, 20 minus shift alpha V1, divide that whole thing by 50 over 20. All right, so it's going to run each of the I values through this formula and produce a corresponding probability. All right, so we have that. We can just jot that down. All right, I'll put it in I'll put it in later. But I could now find different probabilities. So if I were to say, what's the probability that no females would be promoted? That would be 0.00292. And again, when we talk about probability, we talk about just a natural occurrence. So what are the chances that something would happen just based off chance alone, nature running its course? So it's very improbable that no females will get promoted. So if it turned out that none of these promotions were offered to a female, then you would say something unnatural is happening, which means that there's some sort of outside influence that's impacting the results. Right? And same idea, all 10 of them, if all 10 of the females got promoted, then we would look at that and say, well, that's unlikely also. But the good thing about a distribution is you can kind of find the sweet spot of what you would expect to occur, so the expected value, somewhere in this neighborhood. Right? You could also get it from the stats menu, mu, right? The expected value, mu, is equal to 4. All right? So that brings me back to this. The mean of the distribution is equal to nk over n. Right? Now, the notation's a little funky for this one, which I don't really love. And in fact, I've found that it's kind of frustrating to try to use the hypergeometric function in the numworks calculator because just the placement of the constants and the variables. So I tend to just work with this formula as is, right? But regardless, if I needed to compute mu would be equal to, again, nk over n, right? N, the capital N is 50. The lowercase n is 20. And the k value was, where's my k value? K value is going to be equal to 10. All right, so it's this one here. And if you run that computation, you get a result of 4. All right, and you can do the same thing for variance. All right, so you just pop it in, but then just remember they give a variance formula here. Oftentimes we want standard deviation, which would be the square root of that. All right, so just kind of keep that in mind. And just one additional example. Suppose there are 30 students, 20 male, 10 female, applying to the same college. College will accept only 10 students. What's the probability 5 of them would be male and 5 would be female? Right, so here what I'm going to actually do is I'm going to apply a hypergeometric distribution, but I'm not even going to look at the formula. I'm just going to go back to haves and needs. All right, so we have the males and the females. The ordering is really not that important as long as you keep things straight. I'll go males first this time. Females. All right, so we have 20 of the males, 10 of the females. What's the probability 5 will be male and 5 will be female? All right, so boom, 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 and then put it all over the most general case where there are 30 students and they're going to accept 10. All right, and so we would just run this through a computation. So in the calculation app, toolbox, probability, combinatorics, combination, 25, 10, 5, and then 30, 10. And so we get about 0.130. Right. Now, I'll show you very quickly in the toolbox. You go to hypergeometric distribution, so distributions, then find the one that says hypergeometric, and you can see this vast array of craziness. So we have HGeom, PDF, M, capital N, k lowercase n. It really relies on the fact that you know the formula for the hypergeometric distribution, right? So we have, we'll just go back to the previous page. We have the k's, m's, and n's all over the place, right? So if you can keep that straight, you'll know what to plug in where, right? So the m value is whatever the selection is in your first combination. Capital N, lowercase n, that makes up the bottom, so that should be easy enough. And then the k is the top number. So the order in which they chose to put it into the hypergeometric PDF method is not ideal, but we can make it work, right? So my m value, right, so that would be, let's see, I'll use highlighter. So my m value would be this one. My n value would be this one. My k value would be this one. And then the lowercase n, kind of running out of highlight colors here. Go with this one. Would be this. So when I make my selection here, I'm going to type in 5, 30, 20, and 10. And it just seems like I'm randomly taking these numbers and just throwing them in. The one thing that might make a little bit more sense is that you don't have to put in the 10 and the 5 for the other category here, because that's accounted for in the method based off the fact that we already know the first category and the totals. Okay, so there's just some subtraction happening behind the scenes. But it's basically the value of interest. Basically, there's nothing basic about it. The value of interest, the total number, the total number of the first subcategory, and then the amount that make up your sample. I mean, it's very convoluted this way. I think, honestly, instead of trying to focus on the HGOM PDF function, this is probably the better way to do it, just because of all the moving parts to something like this. But if you like this and you can handle it, then by all means. But this is probably the way that demonstrates more understanding.